Well, the next thing that I want to look at then is the power supply, and it's going to take the rest of the day today for us to cover power supplies. We have lots and lots of power supply failures. Lots and lots and lots of power supply failures. Let's look at something here. So page 16 is the article on this. We have lots of power supply failures because the power supply works really hard. It's providing the power for everything else in the monitor. And power supply failures, you can have all kinds of power supply failures. You can have no voltage coming out of the power supply. You can have too much voltage coming out of the power supply. You can have some other weird problems with the power supply. Remember I mentioned to you that the power supply is referred to as the B+ power supply. It's called the B+. It's actually a throwback from the old radio days. Way back when they first had radios, they were, of course, all vacuum tubes. And it actually took 3 batteries to operate a radio back then. You had what we call the A battery, which was a low-voltage battery that operated the filaments, the heaters, that heat up vacuum tubes. Just the picture tube is a vacuum tube. It has that CRT heater. Almost every vacuum tube has a heater in it. And so there's a low-voltage battery that was for the heaters. It was called the A battery. Do you know how you can get like AA cells and AAA cells? Do you ever wonder why you never see an A cell? That was the old-fashioned battery that you used to use in the old radios. They actually still make them for radio collectors. So that was the A battery. Then there was the main battery, the high-voltage battery, and sometimes it was a 90 or 160-volt battery. That was the B battery. That was the main power supply. They called it the B battery. And then there was the C battery, which was what we refer to as a bias supply. You don't really have to know what that means. Well, when we got rid of batteries and we came up with this power supply, we got rid of the A battery and the C battery. Whoops. But we still left bad hand. We still left the term B, meaning, hey, this is the main power source. So that's why we refer to it as the B+ power supply. Well, first of all, I mean, what the heck is a power supply? Obviously, the power for the monitor comes from the AC wall receptacle, the 120 volts AC. But there's a problem with AC. Alternating current is real good for some things and not good for other things. Alternating current is great for things like incandescent lights and fluorescent lights. AC is great for motors and heaters, weed whackers, toasters, hair dryers, stuff like that. Alternating current works great for that. Even the heater in the CRT, that can run off of AC. It's just a little heater, no problem. But alternating current is not good for electronic stuff. Electronic stuff like monitor circuitry and computers and VCRs and televisions and stuff like that, those all require direct current to operate. And so what the power supply does is takes in alternating current and changes it into direct current. It's really a power changer is what it is. Essentially, what the power supply is doing is simulating the DC output of a battery. And in fact, when they first made power supplies, they didn't call them power supplies. They referred to them as battery eliminators because that's what they were doing, is eliminating the battery. We now call it a power supply. So that's what it's doing. Now, in addition to changing it from AC to DC, power supplies might also change the voltage. If you're a slot tech, you're probably familiar with low-voltage power supplies like the 12, 13-volt power supply that powers the JCM WBA bill validator. There's other low-voltage supplies like a 5-volt power supply for the game logic, maybe even a 3.3-volt supply if it's a motherboard kind of based game like a multimedia games or something like that. So in that case, it also takes the 120 volts AC in and lowers the voltage to, let's say, 12 volts DC. So in addition to changing it from AC to DC, it lowers the voltage. It won't always do that, though. For example, there's one monitor with which I am familiar that the power supply takes in 120 volts DC, and the input's 120 volts AC, and the output comes out as 120 volts DC. In that case, it doesn't change the voltage, it just changes it from AC into DC. It is possible also to have a power supply that raises the output voltage, but it's not typical in this industry. Other industries, it's real common. So really that's what the power supply is doing for us. What the power supply is doing is it's taking in the alternating current and turning it into direct current, which is then used by the deflection circuits, the video circuits, all those circuits that we already talked about. Well, before we go any further into this discussion of the power supply, let's take a closer look at alternating current and see what AC really is. And the easiest way to do that is to look at the alternating current in the form of a graph. And what I'm going to draw here is a simple graph that shows time in the horizontal direction versus voltage in the vertical direction. Time versus voltage. This happens to be the same graph that an oscilloscope draws. If you're familiar with the oscilloscope, that's the piece of test equipment with the little TV screen on it, 8,000 knobs, and you got to be like a real bitchin' genius to use it. All it is a graph drawing machine that shows a graph of time versus voltage. Now, don't get me wrong, I like the oscilloscope. I have a scope, and I know how to use it. I love using it. I rarely have a reason to use it, though, quite frankly. With monitor repair, you can pretty much do everything that you need to do, almost everything, using just a meter, as you'll see. So I'm going to draw a line right down the middle of this thing, and I'm going to label that 0 volts. That is ground. Ground is 0 volts. It's our 0 volt reference point. The frame of the chassis, the monitor is ground. Alternating current is always changing polarity. Sometimes it's positive, sometimes it's negative. It's called alternating current because, as you know, sometimes it goes this direction, positive, and sometimes it goes this direction, negative. And it's changing polarity 120 times a second. The frequency of our AC power, of course, is 60 hertz, 60 cycles per second. Well, anytime the current is positive, I'm going to draw a line above ground, and if it's negative, I'll draw a line below ground. And what alternating current would look like, if you looked at it on an oscilloscope, is like this. It starts out at 0 volts and climbs up in voltage. Over a period of time, it climbs up, like it's 10 volts, 20 volts, 30 volts, 40 volts, and so on, until it reaches some sort of peak voltage. But it doesn't stay there. It's only at the peak for a momentary instant in time, and then it drops back down to 0 volts like that. When it reaches 0 volts, it keeps going in the negative direction. This is known as the zero crossing. You don't really have to know that, but it's called the zero crossing. And it climbs down negative, minus 10 volts, minus 20, minus 30, minus 40, 50, and so on, until it reaches a negative peak that's just as far below ground as the positive peak was above ground. And then it turns right around and comes right back up to 0 volts, and that's what one cycle of alternating current would look like. They're supposed to be the same size. That's what one cycle would look like. And then the process is repeated 60 times a second. That's one cycle. That's another cycle. That's another cycle. That's what alternating current looks like. If I were to draw it in a slightly different scale here, more or less like that. Now, this picture that I've drawn here of the AC is technically referred to as a waveform. W-A-V-E-F-O-R-M, a waveform. This particular waveform does have a name. It's referred to as a sine wave, S-I-N-E-W-A-V-E, a sine wave. And I've seen it written both ways as one word, sine wave, or two words, sine wave. So I think they're both equally acceptable. Anyway, so that's what AC looks like. That's what alternating current looks like. If I were to draw a graph of DC, most of you are aware of this, what would the graph of direct current look like? Just a straight line, just like that. Just a flat line, just like that. Why? Well, for example, let's talk about like the output of a battery here. Here's a 9-volt battery. Here's 9 volts. If I measure it now, it's 9 volts. If I measure it now, it's 9 volts. If I measure it now, 9 volts, right? It's always 9 volts. If I measured a week from Tuesday, it's 9 volts. It's always 9 volts, right? So the graph of DC is a straight line. So what the power supply is doing then, in a nutshell, is somehow the power supply is turning this into this. Everybody with me on the concept? So that's really what the power supply has to do for us. All right, so let's see how it does it. The type of power supply that we use in modern monitors has a name. It's referred to as an SMPS, which stands for switched mode power supply. A switched mode power supply. The first thing that has to happen is the AC power has to come in. So there's the AC power comes in and goes through a fuse. That's the schematic symbol for a fuse. Fuse. Okay. And just as a point, just to mention a little point here, not that we're talking about fuses. You see the little dot right in the middle of that fuse? See that little ball of solder that's in the middle of that fuse? A lot of people look at a fuse like that and they go, hey, that fuse is blown. Or they think, oh, that fuse is partially melted. Look, there's a little solder ball on there. Just the opposite, really. That solder ball is telling you it's good. It's just a visual indicator. Because the wire is so thin, they put a little ball there to say, hey, yeah, it's good. You should really use your meter to test a fuse. It's okay to look at a fuse and call it blown, no problem. You pull out a fuse and it's blown to smithereens, sure, no problem. But you should not eyeball a fuse and call it good. You should always use your meter on continuity tester or ohms or something and check the fuse with a meter. You should really pop it out, really, to check it with a meter to see if it's good or bad. I can't tell you how many times I've gone out on service calls only to change a fuse. And it's especially common on these slow blow fuses, not to spend any real time on this, but on some of these slow blow fuses where it has a central element and the fuse is really like this, you know, it's got this whole thing like there, where it blows can be just a little tiny piece of it right there where you really can't see, or on occasion it can blow under the end cap, which it's never supposed to do, but does. And you look at it, it looks perfectly good, but if you meter it, you'll see that it's not. So it's really lame to have somebody follow you only to replace a fuse that you missed. I mean, that's pretty much the most embarrassing thing that can happen. All right, so anyway, so there's the primary fuse. The next thing that it goes through in the power supply is something that you don't really care about, but I'll point it out to you. And if you look on page 17, and in fact, let me see if there's a better view of this. Hang on a sec. No, I guess not. If you look on page 17 at that schematic on the top here, this is a fairly typical schematic. And the AC power comes in here on the left where it says L and N, which stands for line and neutral. Line meaning the hot side of the AC power. The AC comes here, goes through the fuse. And the next thing it goes through is this circuitry, which is a zero failure item. But I'll point it out to you anyway. This circuit, which is made of this coil here, which is labeled L101, believe it or not, C for capacitor, L for coil. Pretty mysterious, huh? But coils are labeled L, named after a guy named Lenz, L-E-N-Z. And there's a little capacitor here and a little capacitor here. Stand by, let me just show you where they are, and I'll tell you what it is, but you can ignore it, but here's what it is. The AC power comes in through this connector, through the fuse, and the next thing it goes through is this circuit, which consists of that's the coil thing right there. It's called a line filter, and these two things, which are actually capacitors. Those maybe are not familiar to you as capacitors, but they're polystyrene or polypropylene capacitors, little tiny capacitors. Really, in my experience, all but a zero failure item. You can see it's a 0.47 microfarad capacitor. You there? But it's not an electrolytic capacitor. It's right across the AC power. Electrolytic capacitors, as some of you know, are polarized. It couldn't possibly be an electrolytic, but it's a capacitor nonetheless. Well, here's the point. That circuit is more or less like this, and I'll draw it quickly on the board, but you can kind of ignore it. It's a coil here, like this, and another capacitor, either one more capacitor here, or in some cases, you'll see two capacitors connected to ground like this. And this is a circuit that doesn't ever really fail. It's called the line filter. When I mention line in this case, what I'm referring to is the AC power line. It's called the line filter. Here's the deal. These power supplies are referred to as switched mode power supplies. In these power supplies, there's a transistor that's switching on and off really, really fast. There's a transistor in these power supplies. We'll look at it in great detail coming up. It happens to be something known as a MOSFET. It's that transistor that you see right there. Yeah, sure. Yeah, Class D amplifier, sure. Anyway, that transistor is switching on and off real fast. I'll tell you in great detail shortly exactly what it does. But it's switching on and off really fast. As this transistor and the power supply itself is switching on and off really fast, and if it switches on and off at more or less the same frequency as the horizontal frequency of the monitor, meaning 31.5 kilohertz for an VGA monitor, it generates a mess of electrical noise. Electrical noise, which is known as EMI. You don't really have to know this. It stands for electromagnetic interference. For example, have you ever been watching TV and somebody in the household turns on a drill motor or an electric hairdryer or a mix master, and sometimes you'll see some electrical interference on the screen? That's EMI, and that comes on the power lines through from the motor brushes. That's where it's being generated through the AC power lines, and that's how it kind of gets up into your television. Well, these switched mode power supplies, as a natural byproduct of their operation, nothing wrong with it, that's just the way they work, they generate a mess of EMI. I mean, they generate a ton of this EMI. To prevent that EMI, that electromagnetic interference, from getting out of the monitor and interfering with the computer in the game or anything, the sound system especially in the game, we have this thing called the line filter. And in a switch mode power supply, that line filter is used to prevent that electrical noise from getting out of the monitor and into anything else. Now, we use line filters all over the place. In fact, if you look in your slot machines where the AC input comes in, it usually goes into a little gray box, which is called the line filter. And in that case, it's used to keep the noise that might be on the line, the AC power line, from getting into the game. Line filters work both ways. They either work to condition the power coming in so that you don't have any interference on that, or in the case of a switch mode power supply, it's used to keep that electrical noise from coming out of the power supply, which is very interesting because if you talk to most technicians, you say, well, what's the purpose of the line filter? I can almost guarantee you 99% of the time they'll say, oh, it just cleans up the power line before it comes into the power supply or the monitor. Normally that would be true, but in this case it's actually used the opposite way to keep the noise from coming out of the power supply. Well, regardless of whether you understand that or not, it doesn't make any difference because this is a really high reliability circuit. Yes, I have seen that capacitor short circuit once or twice and blow the fuse, but in general it's an extremely high reliability circuit. And so that being the case, since we don't care so much how it works as how it breaks, let's eliminate the line filter just for the sake of clarity here. So we have the AC coming in, and AC sucks. We want to make something good. And so the next thing that will happen is it will go to a device that will change it from AC to DC. And that device is something known as a bridge rectifier. Right. A bridge rectifier. Now, again, I wish you guys knew what diodes were. Some of you do. A lot of you do, and some of you don't. A bridge rectifier is made of 4 individual diodes, and what the bridge rectifier does is changes the AC into DC. It's called the bridge rectifier. The bridge rectifier can be made of 4 individual diodes, or it could be a single one-piece bridge rectifier. In this case, we have 4 individual diodes here, and it's kind of unusual because they're all spread around. Make sure I'm pointing at the right things. In this case, we have a bunch of individual diodes. These are diodes here. There's one there. There's one there. Right there. There's one down here. Right down there. It'll either be 4 individual diodes, or it can be a single one-piece bridge rectifier, as it is on this one. Let me just show you what this looks like. not as dumb as I look, you know. And you'll notice I don't hesitate to, stick my hands in it with the power off. I'm not worried about getting a shock. That's the bridge rectifier there, this thing that you can't see any longer. That square, flat, black thing, here I'll center it. That thing right there. A bridge rectifier is four diodes, whether it's four individual diodes or a one-piece bridge rectifier. They work exactly the same way. And what the bridge rectifier does for us is changes the AC into DC. What it does is this. Here's the AC power coming in. We just looked at that, the sine wave. What the bridge rectifier does in a way that I just can't take the time to explain here is it literally takes the negative halves. Here's the positive half cycles, negative, positive, negative, positive, negative. It takes the negative half cycles, which we don't want, and literally flips them up like this. And what we end up with is this. Instead of going positive, negative, where it used to go negative, now we have only the positive pulses. Well, remember the definition of DC, or I don't remember, but the definition of DC is current that flows in one direction. Where the AC was going this way, positive, and then this way, negative, positive, negative. With the bridge rectifier, we only get positive. Positive pulse, positive pulse, positive pulse. Now, it's not particularly good DC. It's certainly not the straight line that we've been looking for. So we're not there yet. It's kind of a shitty DC that we refer to as shitty DC. No, it's not really. It's called pulsating DC. It's called pulsating direct current because obviously it comes out in pulses. Okay. So it's really not the straight line that we're looking for, but at least we're on our way. We no longer have AC. Now we have DC. And now we need to take it one more step, which we'll do right after this break. So far what we've ended up with is just this pulsating DC, which is okay, it's DC. We still have a major problem, though. It drops down to 0 volts every 120th of a second. It drops down to 0 volts, so that's completely unacceptable. This might be okay to charge a battery or something, but it's certainly not okay yet. So we need to add another component to that, and that component is a capacitor, an electrolytic capacitor. Now again, kind of frustrating for me because we spent a little time talking about a capacitor. But what a capacitor is a short-term rechargeable battery that can be quickly charged up and just as quickly discharged. Here's the electrolytic capacitor here that I'm talking about. It's easy to identify. It's always the largest capacitor in the monitor. It is not a particularly high failure item. I've seen them fail sometimes. We'll talk more about capacitor failure tomorrow. But there it is right there. And what a capacitor is a very short-term rechargeable battery that can be charged up in a heartbeat, just instantaneously charged up. It also discharges quickly as well. It charges up really quickly and can also discharge really quickly. Well, when we put this capacitor here, here's what happens. What we had before was this, the pulsating DC. Right here at the peak, there's current flowing out of the diodes. And that current goes to the rest of the circuitry. But at the same time, it also goes into the capacitor to charge it up. So at this point, the voltage on the capacitor is right here at the peak. The output from the diodes then begins to drop. But now it doesn't make any difference because the capacitor is fully charged. And it stays charged until the next peak comes along and kind of tops it back up again. And what we end up with is this, right, the straight line that we've been looking for all along. Instead of it pulsing like this, where it used to pulse, now we have the straight line that we've been looking for. Essentially what that capacitor has done is it's filtered out the peaks and valleys, and we end up with this straight line, which we now refer to as filtered DC. It was called pulsating DC before. Now it's known as filtered DC. And in fact, that capacitor is referred to as the filter capacitor. It's an irregular electrolytic capacitor, but its function is that of filter capacitor. And so what comes out of this is the straight line that we've been looking for all along, which we now refer to as filtered DC. Now, if you don't totally understand that, here's a real easy analogy. Imagine in your car, you're driving around, and you can listen to the stereo. You've got the stereo on, the headlights are on. Why? How does that work? Well, you've got a generator or alternator in your car that's providing the power for all that stuff. As you know, the battery in your car is only to start the thing. Once it's started, you can take the battery out and throw it away, and the car still works perfectly okay. So when the car is running, that's like when the voltage is coming out of the diodes and the voltage is at the peak. When you stop your car, you can still listen to the radio even though the engine's not running. Why? Because here, let's call that when there's nothing coming out of the diodes, it's like nothing's coming out of the diodes. But now that capacitor is fully charged, just like your battery is fully charged when you're sitting there in a parking lot listening to the radio. And it stays charged until you start the car back up and kind of top the battery back up again. So same thing. They put a capacitor in here that's big enough to hold a charge in between pulses. All we have to do is kind of top it up, keep topping it up to replace whatever it is that we sucked out of it during this time period here when there's virtually nothing coming out of the diodes at all. So, same kind of deal. When there is something coming out of the diodes, it charges up the capacitor. When the voltage drops to zero, it's just like the diodes aren't even hooked up anymore. Now the capacitor is acting like a source, isn't it? It's the source of power, and it's the thing that's keeping the monitor working. And in fact, during that time period here, when there's nothing coming out of the diodes, you kind of have a battery-operated monitor. The only thing that's powering the entire monitor is the charge on that capacitor that I just showed you. That's why it's a fairly large capacitor, because for that split second in time, you have a battery-operated monitor. It's the same thing for your low-voltage power supplies that power the computer board. During that time period, when there's nothing coming out of the diodes, you have capacitors in the low-voltage power supply. That's what's powering the computer. It's standard operating procedure. Every power supply in the world is like this. There's only one way to do it, and this is how. So now we have our DC, hooray, we have our filtered DC, and if I were to measure the voltage right here in a normal working power supply, that voltage will be approximately 160 to 170 volts DC. We've got the 120 volts AC coming in, 60 hertz. We run it through the bridge rectifier, we hang this filter capacitor on it, and this is fairly important to know. In a normal working monitor, everything is working perfectly, nothing wrong with it, that voltage right there will be about 160 volts DC. Any questions about that, Frank? Sure there is. So we put in 120 volts AC, rectify it with the bridge rectifier, filter it with the filter capacitor, and that voltage right there is 160 volts DC. Any questions? Thank you very much. Where did we get the extra voltage? What? We put in 120? How did we end up with 160? Pretty weird. Well, first of all, let me explain to you that that's perfectly normal. Anytime we turn AC into DC, the DC that we get out seems to be higher than the AC that we put in to begin with. Wow, that's pretty weird. Let me also tell you that that is perfectly normal and that nothing could ever fail over here to cause that voltage to be too high. The only thing that could fail at this point is a diode or two in the bridge rectifier could fail. When diodes fail, they typically short circuit 999 times out of 1,000, maybe even more often than that. Diodes short circuit when they fail. If they did, it would blow that fuse. Very unusual failure, by the way, but I've seen it way more than once. It's not terribly common. I shouldn't say unusual. I should say it's not terribly common. If the capacitor fails, and this is an important thing to know about capacitors, if the capacitor fails, instead of keeping the voltage constant, and remember this is what the pulsating DC was doing before, right? Instead of keeping the voltage constant, when the capacitor fails, it loses its ability to hold a charge. I wish I had more time to talk about caps because they're interesting. But what it does is it allows the voltage to drop down in between pulses, like that. And we end up with a voltage that's not the straight line we've been looking for, but this ripple line, if we were to look at it with an oscilloscope. And in fact, they refer to this as power supply ripple. This is known as power supply ripple. Sometimes it's referred to as AC ripple because it looks almost like a little bit of alternating current riding on top of the direct current. It's really undesirable. We don't want this at all. And it's what happens when the capacitor fails. It allows ripple into the supply. Well, what that does is causes the voltage to read too low. Nothing could cause the voltage to read too high here, nothing failing, that is. But it is possible that the capacitor can fail and cause the voltage to read too low. One of the symptoms of a bad electrolytic capacitor, that's a filter capacitor in a power supply, is voltage that is too low, not too high. This AC ripple is also sometimes known as hum. It's called power supply hum because if you were to power something with a sound system in it, and the power supply had ripple in it, you would hear a noticeable 60 or 120 hertz hum coming from the speaker. So if you ever have a sound system like your home sound system or slot machine or something like that, where there's a noticeable hum coming from the power supply, one of the causes might be that the electrolytic capacitor in your power supply is losing its ability to hold a charge, allowing this ripple into the supply, which causes the humming sound. It's also possible in your stereo that it's humming because it simply doesn't know the words to the song. So, bada bing, bada boom. So anyway, it's called AC ripple. Now, there is always a little bit of ripple on here. If you think about it logically for just 1 second, in between pulses here, I am drawing current out of that capacitor. And so there is a tiny bit of ripple that's perfectly normal in a power supply. There's nothing we can do about it. That's the way it goes. I mean, that's because current is coming out of the capacitor. Just like when you're parked listening to your radio in your car, surely the battery is discharging a little bit. I mean, it must be. And then when you start the engine, it charges it back up. Same thing here. But in this case, when everything is working normally, that voltage will be 160 volts. And the reason for that is this, in a nutshell, kind of quickly. It has to do with the way we measure alternating current. DC is easy to measure, isn't it? You know, when I measure that 9-volt battery, no matter when I measure it, it's always 9 volts. But how the heck do you measure something if it's always changing voltage like this? I mean, here it's 0 volts, 10 volts, 20, 30, 40, 50, and so on. And it goes up and down and up and down. Well, it turns out that there are several different ways to measure alternating current. One way is to measure from one peak to the other peak, from the positive peak to the negative peak. It's a type of measurement that we amazingly enough refer to as the peak-to-peak measurement of the AC, from one peak to another. But peak-to-peak measurements are generally reserved for what we refer to as non-repetitive waveforms. A sine wave is repetitive. It repeats, doesn't it? It's the same thing over and over and over again. It's a sine wave. But something like audio, for example, if I were to hook up a microphone or a speaker to an oscilloscope, what audio looks like is something like this. Where the peaks are large, high voltage, the sound is very loud. Where the peaks are small, the sound is real quiet. Well, if I'm working on an audio amplifier, if I'm designing an audio amplifier, if I have an audio system like this system with the wireless microphone, I have to make sure that at the very loudest peak, I am not overdriving the amplifier. Because if I do, it will clip. It'll do this. It'll cut off the peaks. It's called clipping, and the sound's all distorted, real funky. If you've ever heard, if you got like a car that goes boom, a guy with a big car stereo, but it's a cheap car stereo and it has it cranked up really loud, it sounds distorted and terrible because it's all clipping. So if I'm designing a system, I have to make sure that I measure the peak to the peak. Look, most of everything else is less than the peak, but I can't clip the peaks, can I? So I need to know what the peak-to-peak voltage is. Okay, well, if you understand that or not, that's okay. So that's called peak-to-peak. But in a repetitive waveform like this, the positive peak is the same as the negative peak. They're supposed to be the same size. So I can actually measure from one peak to 0. That tells me the same thing, doesn't it? It'll be exactly half of whatever the peak-to-peak is. And we refer to that as the peak measurement. But that's still not very informative because 99.999% of the time it's less than the peak, isn't it? It's only at the peak for an instant in time. And so there is a third way to measure alternating current, and it's kind of an average measurement. where we average out the peaks and valleys. We average out the times that it's less than the peak with the time that it's at the peak, and we come up with some kind of an average measurement. And it happens to be what we refer to as an RMS average. You really don't have to know this particularly. You just have to know that the voltage is too high. That the voltage is 160. But it's called the RMS average, and it's some kind of a psycho formula where you take the square root of the peak voltage and you add your mother's age, and if it's Tuesday, you subtract 27 from, or add 27 to it, or something like that. And it turns out to be, and I'm not a math wizard, it turns out to be that the RMS average happens to be 0.707 times whatever the peak voltage is for a sine wave. Not that you really care. Well, the point that I'm making here really is this, that, I can find this thing. Sorry. Well, heck, where's my meter? The point I'm making is this. When you measure alternating current with a digital multimeter like this one, your digital multimeter is measuring the RMS average. If you set your meter on AC volts and plug it right into the wall receptacle, it reads 120 volts AC. That's really an RMS average. A good, normal good meter will show you a true RMS average for 60-cycle AC sine wave. It really peaks at 160 or 170 volts. When that meter tells you it's 120 volts, it's kind of a lie. I mean, it isn't really a lie. It's showing you the average. But when we rectify this AC, the process of turning AC into DC is called rectification. When we rectify it, and then we add the filter capacitor, look where the filter capacitor keeps the voltage, at the peak. So therefore, when we put in 120 volts AC, which is really an average reading, it really peaks at 160 or 170. When we turn it into DC and add the filter capacitor, that's where it keeps the voltage at the peak. So that's the reason why. And this will be absolutely true of any time you have a power supply and you're turning AC into DC. For example, if I wanted to make a 12-volt power supply, if I got a 12-volt transformer, and it would actually be a 12.6-volt transformer, because that's what they make, and I rectified it and filtered it, what would come out is about 18 volts. What would come out is 1.414 times whatever the RMS average is. Not that you care, because you're never going to be doing that kind of mathematics anyway. All I really want you to know is that at this point, this voltage right here will be 160 volts DC. And the only reason I'm mentioning it is so you don't freak out. If you happen to measure that voltage and you go, wow, it's 160, but I only put in 120, something must be wrong. Nothing's wrong. That's normal. Is everybody okay on that? All right. So now we have our yes, sir. Tony. Sorry. What is it? What are you? Troy. I'm sorry, Troy. Troy. Okay. Could you change your name to Tony? Would you mind? Because it'd be a lot easier for me. I'm sorry. Go ahead.
Well, I'm glad you explained that because I wanted to ask, could you sometimes confuse the bridge rectifier with a step-up transformer?
I don't see how. Transformer's a hunk of iron with two coils on it.
Well, I was looking at the 120 volts AC.
But we didn't really change the voltage. This voltage was always here. We just never saw it because the meter showed us an average. If I had a meter that magically showed me the peak, then what I measured here would be exactly the same as over here. All right? Okay. So now we have our DC. That's what we've been looking for. Great. Let's use it. Oh, heck, we can't. Even though we've made our DC, we can't use it to power any of the monitor circuitry. And the reason we cannot is there's several reasons. Number one, remember I mentioned that there will still be a small amount of ripple on this capacitor because it's being discharged in between pulses. Well, if we use that voltage to power our monitor, as this voltage goes up and down, we would see the sides of the picture doing the hula like this. If you ever see a monitor where the sides of the picture are doing like this, you're looking at a bad electrolytic capacitor in the power supply here. It'll be doing this. As the voltage goes up and down and up and down, the whole picture will be doing the hula like this. So that's a bad thing. Additionally, there's one other real important reason why we cannot run that right to the monitor. Even though it's beautiful DC, it's pretty good DC, we can't use it yet. and that is because the AC power might not necessarily be constant. This 120 volts AC can vary plus or minus 10% pretty easily. I'm sure most of us have been in a room and had a compressor or an ice maker or a freezer or something kick in and momentarily the lights dim. And if you're on the res way out at the end of a power run, some of the res power I've encountered is just nasty. Sometimes it's 109 volts, sometimes it's 127. You don't know what's going to happen there. And in the third world, it's really bad. If you go down to Brazil, it's supposed to be 240 volts, and sometimes it's 197, sometimes it's 260. You know, you never know. Mexico, it's supposed to be 120 volts AC, might be 108, might be 132. You never know. Well, the point that I'm making is that even if you have good power, it can vary somewhat. And if the AC line voltage drops and increases, the size of the picture will shrink and increase. So if that happens, what will happen is the picture will overscan if the voltage is too high. If the voltage goes up too high, the picture will be overscanned, as we call it, beyond the edges of the CRT, and will miss part of the picture. If the voltage is too low, the picture will shrink in and we'll see black all the way around, which I don't mind personally, but you know, you don't really want the thing doing this. What if you have a touch screen on it, like in a casino maybe? You know, if the picture changes size, what's that going to do to where your touch points are? Obviously, it'll be completely unacceptable, especially in a Keno game where you only have a little tiny square. Everybody with me on the concept there? So what we have to do now is we have to regulate this voltage. And what I mean by regulate the voltage is we have to make sure that the output voltage stays exactly the same regardless of what's going on the input here. It has to stay exactly perfect. So the rest of this circuit now that I'm going to discuss is fairly complex. It's fairly complex. I really want you to relax. Don't freak out about this, because at the end of this, the bottom line is I'm going to point to just a few parts that might fail that cause these problems. So really, I want you to relax. I want you to relax, 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 relax. The next thing that happens then is we have this 160 volts DC, and we connect it to the primary winding of the power transformer. The power transformer in a monitor is real easy to identify because it's always this large yellow transformer. I don't know why they're yellow, but they almost all seem to be yellow. I've seen a few red ones in old Ceronics monitors, but in general, it's this thing right here. And it's just, again, I wish I had more time to discuss transformers. I usually take about an hour to do it. It's just a couple of coils of wire here, and that's the power transformer. So it's real easy to identify. So there's a coil of wire over here, and then a core made out of a material known as ferrite, which is kind of a mixture of iron and ceramic. And there's another coil of wire over here. This coil of wire here on the left-hand side is known as the primary winding of the transformer. It's called the primary winding. And that's the input side. And on the right-hand side, the output is called the secondary winding. So we have a primary on the left and a secondary on the right. Remember, typically inputs are on the left and outputs are on the right. And the way a transformer works is we put an input on the primary winding, and anytime you run current through a coil, it generates a magnetic field. That magnetic field surrounds not only the primary winding, but because these are wound on the same core, since both of the primary winding and the secondary are wound on the same core material here, that magnetic field also surrounds the secondary as well. One of the ways that we can make a generator is by moving a magnetic field over a coil. As this magnetic field builds up and collapses, it causes current to flow in the secondary winding. This magnetic field builds up and then collapses, builds up and collapses, builds up and collapses on the primary, and as it does it, it creates current in the secondary. The easiest way to think of it is think of the primary winding as like a transmitting antenna, and the secondary winding is kind of like a receiving antenna. Even though there's no direct electrical connection between the two, this is really important, they are isolated. Even though there is no direct electrical metallic connection between the two, we can get electric current to flow in the secondary just by putting electric current on the primary. Now, what the transformer is used for, in general, is to change the voltage. Transformers are used to change voltage, and it's called transforming it. Like, for example, the high tension wires we were talking about before. At the power generating station, that voltage is cranked way up with transformers, sent out along those high voltage wires to the poles at to the substation, where it's lowered down to like 12,000 volts or something like that, or 1,200, I can't really remember. And then it goes to the power lines, the big power poles that are near your house, where there's another transformer. The big round thing that's hanging on there is a transformer that lowers it down to 120 volts, or actually 240, well, 120 and 240 to run to your house. So we use these primarily as power changers. But the important thing is the magnetic field has to move. It has to build up and collapse, build up and collapse, build up and collapse. If I tried to put pure DC on the transformer primary, it would build up a magnetic field all right, but it would be stationary. Once it reached that field, it would stay there. Nothing would come out of the secondary. In order to get an output from the transformer, the magnetic field has to move. If I put DC on the transformer, I would just end up with a big electromagnet, and nothing would come out the secondary. I wish I had a little more time to discuss this, but I just don't. Let's just take this with a grain of salt, because it's almost a zero failure item. I've replaced like 5 transformers in 30 years, so 4 of which smoked. So no big deal there. Well, here we have our DC, and it's connected to the primary side of that transformer. Wait a minute, that's not going to work, is it? If I put DC on the transformer, it's just going to build up a big magnetic field, and I'll have an electromagnet, but nothing will come out the secondary. That's no good. Somehow now we have to chop that up. We have to interrupt this 160 volts DC. And the way we do it is with a special kind of a transistor known as a MOSFET. A FET, or more technically, it's called a MOSFET. Hang on one second. Here's a typical schematic symbol for a MOSFET. The one you see in that image is kind of a weird way to draw it. I'm going to draw it in a more traditional way. This is a transistor just like the other transistor I showed you, and it's a switch. It happens to stand for, don't write this down, I'm not going to bother writing it down on the board, metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. It's a switch. It's just like the transistor switch I showed you before, except that it's a much better, higher quality switch. This regular transistor that I showed you before, which is technically known as a bipolar transistor. Remember, it had the emitter, the collector, and the base. And remember how it worked. When we put 0.7 of a volt on the base, the collector and emitter connected together. Well, this is a MOSFET. It's a much better, faster, higher quality switch, which we use in switched mode power supplies. This is the switch from the switched mode power supply. This is the switch we're talking about. We have different names for the leads. Instead of emitter, this is referred to as the source. Instead of calling it the emitter, that's called the source. Well, think about it. It's emitting electrons. It's the source of electrons. Same thing. Instead of the collector, this lead on the top is known as the drain. Instead of collecting it, it's draining them out. They mean the same thing as far as I'm concerned. And over here, the controlling element, remember it was called the base, and that's what turned it on and off. Remember, we put 0.7 of a volt on it, and that caused the collector to connect to the emitter. In this case, this is referred to as the gate. And it's the controlling element. And all we have to do is put juice on the gate. In the case of the FET, this juice comes from a very important thing, an integrated circuit here, known as the PWM controller. It's called the PWM controller. And for reasons that I'll explain shortly what PWM actually means and what I mean by that. Called the PWM controller. Where is that thing? There it is. Okay. That little PWM controller and the MOSFET are here. And in fact, just to review the whole thing, of course, here's the focus, please. Focus. Focus. There we go. Comes in through the fuse. goes to the bridge rectifier, which are these diodes here, filtered by this big filter capacitor. These are all very low failure items. There's the MOSFET right here. And this little 8-pin guy, which is something you want to keep in stock, is this thing called the PWM controller. I'll tell you what those words mean in just a second. This, I'm assuming, is an MC3842 or 43. Let's see if I can read what it says on it. Is it 42? Could you read it? 3842. Very common part, good part to have in stock. It's either MC3842 or U83842. Just put down 3842 if you're writing this in your notes. It's a real common part, and a sometimes failure. Okay. Now, here's the way this works now. And it's really cool. This PWM controller is turning this transistor on and off. When the transistor turns on, the drain and the source are connected together. And the electric current flows out of our power supply, this nice 160 volts DC that we made, and it runs through the primary winding of the transformer and through that transistor to ground. That builds up a magnetic field. I'm putting DC on this transformer, and it builds up the magnetic field, which surrounds both the primary and the secondary. Then this transistor is turned off, and the magnetic field collapses, and that's when we get an output from the secondary side. For those of you that are familiar with automobile ignition systems, when does the actual spark come out of your spark tower, or your coil, I should say? When your points close or when they open? When they open, don't they? You have the dwell time, the points stay closed. When the points open, the magnetic field collapses on your spark coil, and that's when you get a spark out of the tower. Same thing here. When the transistor's on, it builds up a magnetic field, but we can't leave the magnetic field stationary. Remember, it has to move to get something to come out of the output. Then we turn the transistor off, the magnetic field collapses, and then we get an output from the transformer. And here's the cool thing. Wake up. Here's the cool thing. The longer we allow that transistor to remain energized, the higher the output voltage will be. The longer we allow this transistor to remain energized, the bigger the magnetic field will be, and the higher the output voltage will be. If we turn the transistor on for less amounts of time, it will not build up as much magnetic field, and the output will be lower. Is everybody with me on the concept of that? I'm not talking about how fast it turns on and off. I'm talking about the duration of time that it's allowed to stay on versus off. And I'm going to amplify that in just a second. So by using this transistor then, we've chopped up this DC, and we've made this magnetic field that builds up and collapses, and now we get an output from the secondary side, which unfortunately is now alternating current. By doing that, by turning this on and off and on and off, what comes out of the output side over here is now AC again. What? Oh man, we just spent all this time turning it into DC. Now we've just turned it back into AC. AC is no good for electronic stuff, so now we have to turn it back into DC. So on the output side here, you'll see some diodes. But it won't be a bridge rectifier. It will only be one diode. We only need one diode here. That side will be grounded. Following the diode, what do we have? Filter capacitor. So there's a filter capacitor here. It's important to keep these in stock. 100 microfarads, 160 volts DC. Extremely common value for the output filter capacitor of a power supply. And this is kind of what you see here. Here's the output of the transformer. There's some diodes in here. In fact, there's one right there. Little kind of a oval shape kind of a thing. And then the output filter capacitors. And that'd be these right here, these guys right here. But 100 microfarads, 160 volts is an extremely common value. You should always have those with you because that is a real common failure item. These switch mode power supplies gobble up these capacitors. These need to be super high quality capacitors. Again, we can't take a lot of time to talk about it. These need to be what we refer to as low ESR capacitors. These need to be the highest quality capacitors you can get. These need to be low ESR caps, 105 degree caps. You can get capacitors with two different temperature ratings, 105 degrees or 85 degrees, and that's Celsius, of course. Never, never, ever buy 85 degree capacitors. Never buy, unless job security is good and what you're looking for. If you're looking for job security, get cheap 85 degree capacitors. You know how hot it gets inside a slot machine. That heat just destroys capacitors. It dries out the electrolyte inside, and that's one of the things that causes them to fail. I wish I had more time. I don't. But this needs to be a super high quality capacitor. Anyway, and in some cases you'll also see an additional coil of wire here and another capacitor. The coil is not a failure item, but the capacitors are. They'd both be 100 microfarads, 160 typically. And what comes out of this is the B plus that we've been looking for all along. Now, you'll notice in this case we only have one diode instead of instead of four. And the reason for that is this. If you care, and maybe you don't care, and that's okay if you don't. This is working off of 60 hertz. This is 120 volts AC at 60 cycles per second. When I turn this into pulsating DC, that time period is 1/120th of a second. That's a fairly long period of time. That capacitor has to stay charged for that amount of time. If I use just one diode, what will happen instead of flipping the bottom up like this, if I use just one diode, we only use half of the waveform. What comes out of one diode is this. It's pulse, and then there's nothing here for a whole half cycle. And then a pulse, nothing. A pulse, nothing. But that's okay. The reason we can get away with one diode is that this PWM controller chip, which is telling the transistor how fast to turn on and off, it's not turning on and off at 60 cycles. It's turning off at the same frequency as the horizontal frequency of the monitor. This thing is turning off at 31.5 kilohertz, or whatever the frequency of the monitor is. In fact, they're synchronized together. There's a little loop of wire here. Can you kind of see it? It's hard for me to... There we go. You see this loop of wire that's just looped around the flyback transformer. That's the flyback transformer down there. This guy right here. Well, that synchronizes those two things. It synchronizes the horizontal circuit with the power supply. So this power supply is operating at an extremely high frequency. The point that I'm making here is that even though we now have a bigger gap between the pulses, these pulses are coming along 31,000 pulses a second instead of 120 pulses a second. The amount of time that capacitor has to remain charged between pulses is way shorter, isn't it? Therefore, we can get away with just a single diode, which happens to be referred to as a half-wave power supply. You don't have to know that. Where this is full wave, that's half wave. That's all right. So this is our output. This is our B plus output that we can now use to power the rest of the monitor. And this is our 125 volts DC or whatever it happens to be coming out there. Does this kind of make sense so far? Okay. Now, how much time do I have? Almost none. Now, it is this PWM controller chip that controls what the output is. And it does that by what's known as the pulse width. Let me draw this on the board here. I'm going to draw a simple graph here. This is something you really need to know about. You really need to know about this, not just for power supplies, but for everything in the world of electronics. It's pretty neat. PWM happens to stand for pulse width modulation, M-O-D-U-L-A-T-I-O-N. Pulse width modulation. Modulation. Modulation means change. Oops, went a little too far there. Pulse width modulation. Modulation means change. That's all it means. For example, right now I am modulating the frequency of my voice up and down. Modulation just means change. Like FM radio, frequency modulation. The actual radio frequency is changed or modulated by the audio, modulation. Well, when we're talking about pulse width, what we're referring to here is time. If I were to draw that same graph that shows time in the horizontal direction, and I were to draw a graph of the on and off times of the FET here, it might look something like this. Here's where it's off, then it's on. Off, on. Off, on. Here's where it's off. Here's where it's on. When we talk about pulse width, we're talking about the on time. Are everybody with me on that? If I have a wider pulse, what I really mean to say is that pulse is on for a longer period of time. Well, here's the deal. Let's just say when everything is, and I'm sorry, let me back up for a second. Remember the point of this is that we need to regulate the output voltage. So no matter what happens on the input, as the AC input rises and falls, the output stays at exactly 125 or 88 or whatever it's supposed to be. So let's say when everything is working perfectly, this is how long it's on. It's maybe on for 20% of the time and off for 80% of the time. This is referred to as the duty cycle. It's called CYCLE. It's called the duty cycle. And in this case, let's call it 20% duty cycle. It's on for 20% of the time, off for 80% of the time. Let's just say for some reason, whatever reason, the B plus output were to drop for some reason, drop in voltage, due to maybe the AC power dropping in voltage. This integrated circuit detects that in a way that I'm clearly going to have to tell you tomorrow. This integrated circuit detects that and says, wait a minute, the voltage is dropping, let's increase the pulse width. Well, remember, it's the amount of time that this transistor is turned on that determines the output voltage, right? If I increase the pulse width, it's on really for a longer time, it builds up a bigger magnetic field, and when that magnetic field collapses, it raises the output voltage back up to where it should be. Let's just say for some reason that this output voltage were too high for some reason, which it can't actually do unless there's a failure, due to maybe the AC power going too high. The integrated circuit, the PWM controller, detects that and says, whoa, wait a minute, the voltage is too high. Let's narrow the pulse width. Let's decrease the width of the pulse, meaning, of course, decreasing the time that it's allowed to stay on, and that lowers the output voltage back. How many times does that have to happen? That lowers the voltage back to what it should be. Now, it isn't actually fluctuating up and down all the time. It really stays perfectly constant because, remember, it's doing this 31,000 times a second. 31,000 times a second. This PWM controller is sniffing the output in a way that I'll tell you about tomorrow morning and say, oh, are you too high or are you too low? And it changes the pulse width to accommodate that. It's called PWM, and it's the miracle of modern electronics. For example, if you have a variable speed battery operated drill, a Makita drill or something like that, or any brand obviously, when you pull in the trigger, it goes faster and faster and faster, and what you might think to yourself is, oh, it's putting more voltage on the motor, right? Let's say I have a 12-volt system, a 12-volt battery. You might think to yourself, this would be incorrect, if I pull in the trigger a little bit, I'm putting 2 volts on the motor, 3 volts, 4 volts, 5 volts, and the more voltage you put on it, the faster it's going. Totally incorrect. What you're putting on it is pulses. If you notice carefully, when you first pull in the trigger, it kind of sings, doesn't it? It goes beep. And when you pull, and that's the pulses. When you first start pulling in the trigger, it puts narrow pulses on it of 12 volts. It is 12 volts, but it just puts a little pulse on it. The more you pull in the trigger, the wider the pulses get. So, for example, the trigger is pulled in halfway. You're now at 50% duty cycle, half on, half off. The motor's running at half speed. The more you pull that in, the wider the pulses get, until eventually when the trigger's all the way in, you have the full 12 volts on the motor. If you got some patrons in your casino that have an electric scooter, electric wheelchair kind of a thing, they've got a joystick and they push it around. If you listen carefully, usually you can hear the motor singing beep, like this. The further they push the joystick, the wider the pulses go to the motor. Or, if you've ever seen those fancy schmancy cars where you get out of the car and close the door and the dome light stays on for a while and then it kind of dims out over a period of time, You might say to yourself, oh, well, the dome light is dimming. I must be putting 12 volts on it when it's all the way on, or 9 volts, 7 volts, 6 volts, and so on. That's not what's happening at all. When you first turn the dome light on by opening the door, you have 12 volts on it. After a period of time, it starts to drop that voltage out a little bit. If it drops the voltage out for 20% of the time, and this is happening real fast at 100 hertz or faster, the little filament in the light bulb doesn't cool down instantly. If we're giving it 80% of the pulse time, it's 80% bright. Over a period of time, it just keeps cutting down on the amount of time that it's on and off. 50% duty cycle, half on, half off, the bulb's half brightness. You get what I'm saying? Or, do you like listening to MP3s on your computer? You know, who doesn't? You know, I mean, everybody likes MP3 music. But how the heck do you get analog music out of a digital computer? Remember, analog looks like this, right? And digital computer is just on or off. What comes out of the computer really is PWM. Wide pulses, narrow pulses. This is what's coming out of the computer. All we have to do is take a PWM output, hang an electrolytic capacitor on it to ground, and what comes out is music like this. The wider the pulse is, the higher the voltage is. The narrower the pulse is, the lower the voltage is. That's all it is. You will see pulse width modulation all over the place. Anytime we need to control, not anytime, often when we need to control motor speeds, brightnesses of lamps. Oh, well, Williams is a good, any of the new games. You know the LEDs and lights where they're flashing and going on and off and bright and dim? They're not changing the voltage of those lamps. There's always, whatever the voltage is to the lamps, we're pulsing it. When we want the LED to be dim, or the light bulb, incandescent light bulb, to be dim, we send it narrow pulses. Where we want it to be bright, we send it wide pulses. You're going to, pardon me?
Making music.
Oh, we're making music, yeah, all that kind of stuff. So PWM, it's really a miracle. It's just fantastic. And the more you look around, the more you see it. You just see it everywhere. Like the speed control that controls the tape machine here, that controls the speed of the tape going through the camcorder. Same thing, pulse width modulation. And so that's how we can get an exact perfect B plus out, regardless of how this goes up and down. And that's basically how it works. The only thing we have to look at, and I'll just have to cover it tomorrow morning, it won't take me very long, is, you can ponder this or read about it tonight, how do it know? How do it know? How does the pulse width modulation controller know what's going on out here? Certainly it must have to know, shouldn't it? I mean, if that voltage is too high, something has to tell that chip that it is too high. If it's too low, something has to tell the chip that it's too low, and we'll find out how that works first thing tomorrow morning. When we last left our hero yesterday, and we're almost done with this, we were talking about the switched mode power supply. And just by way of really, really quick review, remember what we did was took our 120 volts AC in, 60 cycles per second, of course, 60 hertz power. AC is okay for some things, bad for other things. Let's turn it into DC. So we do that with the bridge rectifier that turns it into DC. That's not very good DC. It's that pulsating DC. So we always add this electrolytic capacitor, this filter capacitor, following the bridge rectifier. Now we have this DC, and if you recall, this unregulated voltage right here is approximately 160 to 170 volts DC, depending on what your line voltage is over there. Gee, that's neat, it's DC, and we could use it maybe, but not. And the reason, remember, that we can't use this voltage is that it is unregulated, meaning that as the AC power rises and falls, so would the output voltage, and naturally that would, well, not naturally, but that would make the picture larger and smaller as the line voltage increased or decreased. And so we certainly don't want to have a monitor whose picture is changing size, especially in a touchscreen situation. So we have to regulate the voltage, and as you recall, the way we do that is by the amount of time that the FET, the MOSFET, the switching transistor in the switched mode power supply, is allowed to remain energized. As you recall from yesterday, the longer that transistor is on, the bigger the magnetic field will be, and then when the magnetic field collapses, we get a higher output voltage. If the transistor is on for a less amount of time, a shorter period of time, then the magnetic field is not as big, and when it collapses, causing the output voltage is not as high. And as you recall, that's a scheme known as pulse width modulation, or PWM. And this is the little integrated circuit. That's the PWM controller chip. There are several different kinds, but the most popular one that you'll see is this small little 8-pin dual inline package, and the part number, typical part number, is 3842. I showed it to you previously. It looks the same as it does the last time I showed it to you. And it's this little 8-pin integrated circuit right there. Now, it's a part number 3842. Or 3843. Through experimentation, they seem to be identical. I've replaced 3842s with 3843s, and they work just fine. One thing you should know about integrated circuit part numbering, for those of you that are unfamiliar with this, and it's all pretty new to you, you may see different two-letter prefixes on the part number. For example, here's the PWM controller right here, and it's a part number 3842. Oops, 38. Yep. 3842. It may be, you'll see two different two-letter prefixes on it depending on who makes the part. It can be an MC 3842. It could be a UA 3842. It could be a KA 3842. It could be a TL 3842. Whether it's a Texas Instruments or Motorola or whoever makes the darn thing, they'll put different two-letter prefixes on it. In general, in integrated circuits, in general, you can ignore the first two-letter prefix. That will change. It's really the 3842 that you're interested in, and that is a sometimes failure. Of all the things that we have here, let's see what fails. And the things that fail, as I mentioned before, are it is possible that the bridge rectifier might fail. And it's not very common, but it does happen sometimes. If the bridge rectifier fails, bridge rectifiers will always short circuit and they'll blow the fuse. In this case, and I can show you a little better now, the bridge rectifier is this guy right here. If we look at this power supply, here's the bridge rectifier. It's a single, where's my finger? It's a single one-piece bridge rectifier. It's this long, skinny guy right here. So the AC power comes in, goes through the fuse, which is right here, goes to the bridge rectifier, which is right here, and then always near the bridge rectifier, you see the big, giant filter capacitor, the largest capacitor in the monitor. Real easy to spot that. Not a high failure item. That capacitor, that big filter capacitor, is not a particularly high failure item. Have I replaced them? Oh, yeah. But in 30 years, I replaced like 4, probably, maybe 3. I can't even recall exactly. It's not very common. And then the yellow transformer, that is the power transformer. Over here on the output side, we've turned it back into AC. We've taken the AC, turned it into DC, but then we turned it back into AC. Boy, that seems like a weird thing. Why would we want to do that? Well, remember, that's kind of the way we have to regulate it. That is to say, the pulse width here determines what the output voltage is, but what comes out of a transformer is AC. We can't do anything about that, so we turn it back into DC. The B-plus power supply and the other power supplies are just about the only thing you'll ever measure with the power on, typically in a monitor. I try to do everything in a monitor with the power off, and it's not like I'm worried about getting shocked. What I'm really worried about is accidentally slipping with my meter and shorting things out. This is really an important consideration, a kind of a philosophical look at electronic repair. If I have two ways to do something, power on and power off, I'm always going to go with the power off method if it tells me the same thing. And again, I'm not really worried about getting shocked at all. I've been shocked a bunch of times, and it hasn't done a thing to me. But the thing that I'm worried about is accidentally shorting my meter leads across some components and letting the smoke out of the part. And that's a really bad thing because, as most of you are aware, there is a certain amount of smoke that's built into every electronic component. It's only when you let the smoke out that they don't work anymore. So it's important to keep the smoke inside. And that's supposed to be a joke. Good morning, it's a joke. All right, but it's true, yeah. And here's the deal, and here's really the thing. The types of failures that we normally see are the same kind of failures over and over again, as I will be going through in the next 3 hours. All the stuff that fails, we'll talk about how it works and how it fails. But as I mentioned previously several times, outputs fail the most, like the video output transistors on the neck board of the monitor that drive the CRT. They work hard, so they fail a lot. So those kinds of failures are straightforward and easy to find. But the kinds of things that fail when you short stuff out and run juice into parts that's not supposed to have juice running through them is completely different from the kinds of normal failures that you see. And it makes your troubleshooting a whole lot more difficult. I mean, way more difficult, because things fail that just don't normally fail at all. You can blow integrated circuits that are normally completely reliable. You can open resistors that would normally never fail in a million years, and so on. So I try to do stuff with the power off. But one of the things that you have to do with the power on is measure the power supply voltages. Not only the B plus voltage, but the power supply, as we're going to see shortly, will also create some other voltages as well. And this is done simply by adding extra windings on the secondary side of the transformer. As you recall, the input side over here is known as the primary side. And over here on the right-hand side, inputs on the left, outputs on the right, is the secondary side, which is the outputs. Well, we have a lot of different voltages that we need in a monitor, and we're going to see what those are today. We need the B+, that's the main power supply that, quite frankly, powers the horizontal output circuit, as you'll see. There's a 24-volt, might be 26, might even be 30-volt power supply. That's going to go to the vertical deflection circuits. That wasn't very good at all, was it? Sorry. Yes, sir? Sorry? Velcro. I got your Velcro right here. Velcro this. Velcro this, you know what I'm saying? All right. So we have this 24-volt, might be 26, that goes to the vertical output circuit, actually. Goes to the vertical output circuit that drives the deflection coil that makes the beam move up and down. There's also a 12-volt power supply, and that 12-volt power supply powers virtually all the other integrated circuits. That is to say, it also powers, the 12-volt power supply powers part of the vertical deflection circuit. Part of the video amplifier, like the LM1203 video amplifier chip that we looked at yesterday, is powered by 12 volts. And the sync amplifiers and some other stuff can also come off of the 12 volts. So this is a low voltage supply that powers some of the integrated circuits on the board. You'll even see, when we'll look at it in just a minute here, a 6.3 volt power supply that goes to the heater. You'll see how all that works. So we have a bunch of these outputs here, and we have to be able to measure those outputs to see what our voltage is. This is the big deal. When you first start working on monitors, you might even know what you have to do. Like, for example, I get to a dead monitor. Well, let's measure the B plus and see what it is. Okay, great. Ooh, where do I actually do it? And that's what I want to show you now. Let's take a look at where you actually do it. And where you want to do it is, let's say, right here. So what you're looking for is a physical test point someplace on the board itself where you can put your meter lead and measure that voltage. Well, we've got a couple of places that we might be able to do this. And just for the sake of discussion, let me eliminate that coil there, because that's not in every monitor. We could measure it right here at the positive side of that filter capacitor. Wow, well, I should have B plus there, shouldn't I? Right? That makes sense. Ooh, but not. Because the filter capacitor is mounted like this on the board. The leads come out the bottom of the board. How am I going to get to that with a meter without flipping the board up with the power on? Man, I don't want to do that. What I'm looking for is a convenient place that from the top of the board I can measure the voltage. In some cases, they'll actually put a little test point, a little piece of metal sticking out that you can touch your meter probe to it. But by and large, really what you're looking for is the cathode of the diode, because the diode sticks out above the board like this. So all I really have to do is look for the striped end, which is the cathode end of the diode. That's where my B plus is. So let's take a look at let's take a close look at that. This is really pretty standard, and you see this on every monitor, really. They all kind of look the same. When you look at a power supply, it becomes obvious where the power supply is, first of all, because you see the yellow transformer, you see the big capacitor. So again, in this case, AC power comes in here, goes through the fuse, goes through this thing I mentioned called the line filter, which doesn't really fail, so you don't have to worry about it. That removes the EMI. Then the bridge rectifier turns it into DC, and there's the filter capacitor that filters it. Then that's connected to the primary winding of the transformer. And then the transistor or device that's mounted on the heat sink near the transformer, I don't care what kind of monitor it is, they're all the same, will be the FET. Now, this particular design, as we'll see, the FET and the integrated circuit are actually combined into one device. This thing that you see sitting on the heatsink here is actually an integrated circuit module. This is not just a transistor. If you look carefully at the bottom, you can see that there's like 5 legs sticking out the bottom of this thing. Since all these power supplies need a FET and the PWM controller chip, that's how they all work, they just said, hey, let's put both of those parts in one thingy, and then we just have one thingy there instead of having the little 8-pin chip plus the FET. So it makes manufacturing a lot easier. And troubleshooting, too, because if it were to fail, you just replace the whole thing as a unit, and away you go. So the FET switches on and off, switching the current on and off across the primary side. So as you can see, all of this stuff here, this is the primary side of this power supply. It's all from here to here is the primary side. So the secondary side must be the other side, and it's real easy to recognize it because what you see is a bunch of diodes and filter capacitors. You see a diode here. You can see the cathode end is there, the striped end. There's another diode here. You can see the cathode end is the striped end right there, so that would be a good test point. There's another diode down here for another power supply with the associated capacitors. So it's real easy to identify where you're going to actually measure the B+. All you have to do is ground the black meter lead to the chassis somewhere, and with the power turned on, carefully, ever so carefully, touch your red meter lead to the cathode of the diode and measure the voltage. I mean, that's all there is to it. Again, it's a little frustrating for me to do TechFest because in my regular class, it's like, hey, come on down, everybody, let's try measuring the B+, and everybody does it, and they go, well, that's easy. And then for the rest of your life as a technician, you're going to be doing this again and again. You're going to be measuring the B+ like a lot. Because the B+ tells you certain things about the health of the monitor. If I get to the monitor and the screen is blank, well, why is it blank? You know, is my B+ there or isn't it there? I mean, after looking at the fuse, the next thing you kind of got to do is check the B+. If I have no B+ coming out, well, that sure explains why the screen is blank, doesn't it? I don't have any power to the monitor. And you'll do this all the time. It is, as I mentioned, it's one of the few power on measurements that you ever have to make is checking all of these different power supplies at the output of the power supply, checking all these different outputs to see if they're there. Any questions so far? Does that make sense? Again, I mean, I'd love to have you all come up and do it, but we just don't have the time here. Yes, sir.
Are you checking just that single diode, or are you going to check all 3 of those?
I would typically hop down the power supply and see what they all were. However, there are sometimes some kind of assumptions that you can make. For example, if the B+ is there and it's perfect in voltage, that tells me that the whole primary winding is good and all that circuitry is good. If I were to have some problem with the 24 or the 12 or whatever, it would have to be a secondary problem, wouldn't it? And there's not really much that can cause that. You'll see fairly often, and it's in this month's Slot Tech magazine as well, fairly often in series with the output, you'll see a current limiting resistor here. These will typically be fairly low in ohms. This might be a 0.47 ohm 5-watt resistor. This might be maybe a 1.2 ohm 2-watt resistor. We're going to talk about these in just a little bit when we start talking about the vertical section because there's a very interesting failure when the vertical output chip fails, which is powered by this power supply. it draws too much current across that resistor and open circuits the resistor. And I'll tell you all about that when we get to the vertical section, because that's an easy fix. That really is confusing if you don't know what you're looking for. Once you know what you're looking for, it's a piece of cake. It's really, 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 really simple. Frank has a very good question. Where's the best place to put ground, to put your meter lead on ground? If I had a meter handy, I would show you. Hang on a second. I'll find my digital multimeter. Hang on one sec. I don't want yours. I want mine. Mine's more gooder than yours. Because mine's a fluke. Ooh, I have 2 flukes. Okay. Frank's question is a really good question. You have 2 meter leads. One's a red lead and one's a black lead. The black lead needs to go on ground somewhere. Well, a lot of people just use the metal frame. You typically can use the metal frame as ground. I've run into a couple of problems on weird, obscure monitors, you probably won't see them, where the ground of the electronics wasn't really the same as the ground on the metal frame, exactly. And so I usually try to find something that's on the chassis itself that's ground. Well, I want to point out one quick pitfall that you might run into, and make sure that you don't do this. You see a fair number of heat sinks on a monitor. Heat sink, as I showed you before, these finned aluminum guys, or gals, I guess, I don't know if they have a sex, that dissipate the heat, that help dissipate the heat. Well, a lot of people will assume a heat sink to be ground. Never, ever assume a heat sink to be ground. Never, unless you check it with a meter or something. And the way I typically do it is, I put my meter on the continuity beeper. So it just makes a beep, the continuity ohms, whatever it is. And this is not mounted in the frame at the moment. But typically I'll start by putting 1 meter lead on the metal frame and then just start touching the heat sinks themselves. If a bunch of them are connected to the metal frame, those must all be grounded together. Now, in this case, what I would do is this. I would pick some kind of a heat sink where I could put my meter lead, like this one. I don't know if it's grounded or not. What I try to find is, I try to find a little hole, someplace maybe where you can stick the probe in there and it'll stay. Like this little hole right here, maybe, where a screw might normally go in. Like that. Oh, wrong lead. So I don't have to bother with that. I don't have to worry about holding it on. It'll hold on by itself. And then I simply check continuity to the other heat sinks. So, for example, if I have continuity between here and this heat sink, which I do, those are probably grounded. Let's see if this heat sink over here has continuity. Oops, it doesn't. Are you with me on that? So suppose you said to yourself, oh, well, I'll just ground it to that heat sink. And you put your black meter lead on that heat sink right there. That's totally not ground at all. That heat sink's floating. So every measurement you make is totally screwed up. Nothing makes any sense. It's very, very confusing. Is everybody with me on that? It's really important. If you can verify that a bunch of metal stuff, basically, is all hooked up together and all continuity, it really has to be ground. Is everybody okay on that? I can't tell you how many times I've seen students confuse the heck out of themselves just because they didn't quite know where to put the ground lead. So that was a really good question, Frank. So it's really just a matter of putting the black lead on ground and then using your red meter lead to touch typically the cathodes of the diodes. Or, for example, in this case, if this was, let's just call this resistor 101, R101, and that resistor physically looks like this. If I can just put my red meter lead on that side of the resistor, that's that point right there, then I'm checking the B+, aren't I? Or that point. It really doesn't matter. You can go on either side of one of those low ohm resistors. It's pretty much the same voltage on either place. Okay. This is Really, really, really critical that you do this. I strongly suggest, I really strongly suggest, when you guys go back to your shop, if you pull out a monitor and start probing around and at least check the B plus on a good working monitor so you see what it's like. Do it as soon as you get back home so you don't forget what this is all about. Once you do it, you'll go, oh, that's simple. It's really nothing to it, but it's just like anything else. I absolutely remember the first time someone showed me how to open up a slot machine and pull the hopper out. And I went, wow, isn't that amazing? It just pulls right out. But if you had asked me how to do it beforehand, I'd have gone, I don't know. I didn't even know the coin tray came out like this. So it's just like anything else. Once you do it once, you go, oh, okay, now I know. No problem. Now, one last comment about the power supply and the way it operates. And this is, what I'm about to tell you is something that can really, really help you fix a ton of stuff that would otherwise be really confusing. Okay, this is a real important thing to know. This little bit of knowledge has enabled me to go to monitors that people have had all kinds of problems with, and in 2 seconds it's diagnosed, and in 5 minutes it's fixed, and everybody thinks I'm a dang genius, and I'm not. It's just like a common problem that happens all the time. And here's the problem, and this is really important to know about. Really, 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 really important to know about. In a monitor, if something fails and the high voltage goes too high, the high voltage at the second anode of the CRT, the high voltage that ends up at the other end of the second anode connector right here, if that goes too high for some reason, the monitor turns into an X-ray machine. We talked about the leaded glass and all that stuff previously, but despite the lead in the glass, if the high voltage goes too high, the monitor will emit X-rays, what they call soft X-rays. That is a health hazard, and therefore there is a circuit that's mandated by law in almost every monitor built called the X-ray protector. It's called the X-ray protector. There is an article, don't turn to it, there's an article in your yellow handout in the back on X-ray protection. Don't turn to it now, make a bunch of noise. It's either called the X-ray protector, or in some cases it's referred to as high voltage shutdown. High voltage shutdown, X-ray protector, protect, shutdown, something like that. And what this circuit does is if something fails and the high voltage goes too high, it turns off the horizontal deflection circuit. Well, we know that the horizontal deflection circuit drives the high voltage, doesn't it? It drives the high voltage unit. So if I kill the horizontal deflection circuit, I kill the high voltage, and I take away the X-ray problem. Is everybody with me on that concept? Okay. So what could cause the high voltage to go too high? Well, it's a power supply failure. If the power supply fails in any way such that the B plus output rises too high, the monitor, all the voltages will be too high, of course, including the high voltage, the EHT, and then the monitor shuts itself down. The symptom is really interesting. The monitor comes on for a split second and then shuts itself down. It's not on long enough for you to see any kind of an image. But you know how you can hear that static sound that monitors kind of make when they first come on? You hear that sound. And actually you hear it really loudly. You won't hear this on the casino floor. You'll only hear it in the shop. But it'll be quite loud, really louder than normal, because your B plus voltage is too high. So you have this really loud static buildup. And then if you listen carefully and you know what you're listening for, you can hear the static dissolve. You can hear it go away. I kind of refer to this as a dissolving curtain of static, kind of. You can hear it on a regular monitor, too. Just take any monitor that's on, and when you unplug it, you'll hear it go crackle, 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 crackle as the high voltage dissipates. So that's the symptom, anyway, of when it enters X-ray protection. I'm going to show you a neat little trick for determining that later on this morning. I'll show you a really cool trick for determining that it has come on and gone off. I can hear it. I know what I'm listening for. And once you hear it, you will know what you're listening for. So when this thing goes into X-ray protection, the monitor is completely blank. And what causes that is some sort of power supply failure that causes the voltage to rise too much. Is everybody with me on that? Okay. Now, when we last left this thing yesterday, as you recall, we were talking about this circuit, and we said, hey, look, somehow this chip has to know what's going on the output. It's regulating the output. Remember, if the output goes up too high, the integrated circuit makes the pulses narrower to bring it back down. If the output is too low, it makes the pulses wider to bring the voltage back up. How do it know? And the way it knows is that it needs some kind of feedback. So obviously it needs some feedback from the output here into the chip to tell it what's going on. Well, we can't actually connect this output into this chip. And we can't do that for a couple of reasons. Number one, the B plus output might be 100 volts or 125 volts DC or something. This is a 12-volt chip. That would be a bad idea. We don't want to run 125 volts into a 12-volt chip. But then you might say to yourself, well, we could just put a resistor in there. I mean, we could take this output, run it through a resistor to cut the voltage down, or a couple of resistors, and run it in there. Ooh, would that work? Well, not that either. A real interesting thing about the way these power supplies work, and it's really important to know, especially if you're like going to be a hotshot technician and be the monitor tech at your property, the primary side of the transformer is completely isolated from the secondary side. There is no metallic connection between these two. There's only a magnetic coupling between the primary and the secondary. Nothing on the secondary side can touch anything on the primary side. They even have completely separate grounds. You'll notice, for those of you that are hip to electronics a little bit, I drew a chassis ground symbol here on the board. Chassis ground. Oops, my battery's dead. I drew a chassis ground on the board here, but over here it's like an earth ground or some other kind of a ground. The primary side here cannot touch anything on the secondary. If any part over here touched any part on this side, smoke and flames would ensue. It would just vaporize stuff, and it would be a real bad thing. So they're completely isolated, and yet somehow this circuit has to tell this circuit what's going on. And the way we do that is really a clever thing. In addition to the secondary outputs that we see on the power supply, 125, 24, 12 volts, there is another output, and it's here. This is a secondary winding. Remember, I've said, though, inputs are on the left, outputs are on the right. But I also mentioned there are some exceptions to the rule. This is a secondary winding. It is an output. There's only one input, and it's here. This is an output just like these are. But the reason it's drawn over here on this side of the transformer is, as you're going to see shortly, we're going to take that voltage and run it into here. So if I could draw it over here, but then I would just have to run a wire around the thing and up like that. And so that's stupid. Why would I do that? So, we try to make schematics as easy to read as possible.
Would it read the same as the 2 plus 1?
No. Let me get there. Now, what this is a sample winding that is directly relative to these other outputs. In other words, this is a winding, just a few turns of wire wrapped around the same core. If these voltages go up, this voltage will go up, won't it? It's on the same core, it's the same magnetic field, of course it will. If these voltages go down, this voltage goes down. So this winding, we'll make this, just for the sake of discussion, and this will vary depending on the type of monitor that it is, let's call this a 12.5 volt DC winding. Our B plus, for the sake of discussion, is 125, so this is 1/10 of that. For every volt that comes out here, 1/10 of a volt comes out here. Everybody with me on the concept? Nice low voltage. We'll use the primary ground for that. Now, this is AC. I misdrew that. That's 12.5 volts AC. Remember, the output of a transformer is strictly AC. No DC comes out of a transformer. Well, AC, remember, it's hard to measure it. Remember, we talked about AC yesterday. It's always changing voltage. It's difficult to deal with. Let's turn it into DC. So let's take this output and run it through a diode. Like that. Just like we have over here. The diode turns it into DC. After a diode, what do we always have after the diode in a power supply? The filter capacitor. So we hang a little filter capacitor on here. It's not very big. It's only maybe 10 microfarads. Might be 100, might even be 1. Depends on the quality, well, it depends on the design. I shouldn't say the quality of the design. Depends on the design. Now what we have is something, gee, that looks like a power supply, doesn't it? Right? A transformer, diode, capacitor. Transformer, diode, capacitor. And in a way, it is a power supply. It's making DC, except that we're not really going to use it to power anything. This is making a DC voltage, and let's just call it 12.5 volts DC. That's a reference voltage that's directly proportional to this one. And then this nice DC, which is easy to deal with, is sent into an input on this chip called the voltage reference input. VREF, voltage reference input. And the voltage reference input then is what is telling the integrated circuit, the PWM controller chip, what's going on the output. In other words, if the PWM controller integrated circuit sees 12.5 volts DC on this voltage reference input, then it knows for sure that we have 125 volts DC coming out of the power supply. Does that make sense to everybody? It's really clever. I mean, I think it's really a cool system, because what it enables us to do is measure or determine, anyway, infer what's going on here without touching it. We're not touching that at all. We've just thrown a winding on this thing, and it's directly proportional. So now here's what happens. As we went over yesterday, just for the sake of discussion, let's say that the output were to drop in voltage. Well, that, of course, makes this voltage drop. The integrated circuit sees that, increases the pulse width, the on time of this transistor, boosting up the magnetic field, boosting up the output to what it should be. Likewise, if the output is too high, then the reference voltage is too high as well. It follows suit. And it detects that, cuts back on the amount of time that the transistor is allowed to remain energized, and the output goes back down. It's pretty cool, isn't it? I mean, I think it's cool, but I'm a nerd, so, that's okay. I love electronics. I just love it. I've always done it. I just love electronics. It's so interesting the way it works. Okay, now, that having been said, gee, Randy, why are you going through this? What the hell breaks? What the heck breaks in this thing? Well, here's the deal. Here's the magic. Capacitors fail. Electrolytic capacitors fail all the time. A little later on, we're going to go over the vertical deflection circuit in the next hour, and we'll talk more about electrolytic failures. But they fail all the time. And as I mentioned yesterday, when a capacitor fails, instead of keeping the voltage constant, it allows the voltage to drop. Do you remember that from yesterday? I said that this one of the symptoms you get when you have a bad electrolytic capacitor in a power supply is low voltage. Well, this capacitor fails. That capacitor fails. When that capacitor fails, that reference voltage drops. The output's still perfect. Nothing wrong with it, but this voltage drops. If the reference voltage drops, what does the PWM controller chip think is happening over here? It thinks that the voltage has dropped. What's it going to do? It's going to increase the pulse width, isn't it? It's going to say, well, I got to bring that voltage up. It can do the only thing it can do is increase the pulse width, and it shoots that thing through the roof, man. And all of a sudden, the B plus becomes 145 volts, or 150, or 160, or whatever it happens to become, depending on how bad that capacitor has gotten. When it reaches a certain threshold set by some potentiometer, the X-ray protector setting potentiometer on the board, when it crosses that threshold, it trips this thing called the X-ray protector, which I'm hoping I'll have time to cover, but I don't believe I will, but it's in your book. And that shuts off the horizontal circuit, which kills the high voltage. So you get to the monitor, you plug it in, it goes, and then goes right back off. It never warms up or anything like that. And you go, oh, X-ray protector has triggered. If you didn't know that X-ray protector circuit existed, you'd really be in trouble, wouldn't you? Because you'd hear it come on, and then it would go off, and you'd be going, oh, I got a bad solder joint on that thing. What's going on, man? It comes on and goes off. I must have a bad solder joint. And you turn the board over, and you resolder every solder joint, especially on the flyback transformer, and you try it again. It comes on and goes off, and you go, dang it, it's got to be an intermittent problem because it comes on for a split second, but then it shuts off, and you start banging on all the parts with the handle of a screwdriver, which is actually one of my favorite things to do. When you have intermittent problems, handle of a screwdriver, you start banging on stuff. If even a problem comes and goes, then you know you have a bad solder joint or a broken leg on a part. So you do that for about 2 hours. You end up resoldering every solder joint on the bottom of this thing 3 times. It still has the same problem. But once you know that the X-ray protector circuit exists, when you hear it come on and go off, and again, I'm going to show you a little trick for determining that later on, you say, oh, X-ray protection. What is the one thing that causes typically it to go into X-ray protection? The power supply has gone over voltage. What typically causes that? Well, in many designs, it's like this. In others, it uses a different scheme. But many designs, it's this kind of a thing. That capacitor has failed, and that's what you're looking for. So what you're looking for typically, physically on the board, is simple. You don't even have to pull out the schematic or anything. I mean, this is so easy. It's just amazing. Let me show you. Locate the PWM controller integrated circuit, which is that little 8-pin chip right there. That's the 3842. Somewhere nearby, you will see 1 or 2 or some small capacitors. Well, heck, I don't know which one of those is the voltage reference capacitor. I don't care. I'm just going to change all 3 of them all at once. Why not? One of them is bad. And even though the other 2 might not be bad now, they've all been subjected to the same heat. They're all the same age. If one's going bad, the others could conceivably be on their way out. And it's one of those few places in electronics that you can do preventative maintenance. Generally speaking, in electronics, you can't do preventative maintenance because it's working. It's broke. One day it's working, the next day it's broken, and then you fix it. But in the case of electrolytic capacitors in a monitor, these are super common failures. And when you start having capacitor failures in a monitor, it's often several capacitors or more that are on their way out. They may not all be so bad that they're causing the problem, but they're all kind of on their way out. Some people, once they have the monitor pulled out and the bench in front of them, if they have a mess of capacitors, they just start changing a bunch of them all at once. That's okay too. But what I'm saying to you is this. You get to the monitor, it comes on, goes off. X-ray protection. You might think to yourself, oh, I have a problem with my horizontal circuit because it drives the high voltage. That's not where your problem is. The high voltage has intentionally been shut down by the X-ray protector due to a bad power supply, due to a bad 15-cent electrolytic capacitor, which you will find located somewhere near the 3842, as you see there. And so that's really the bottom line. No intelligence required. You get to the thing, it does those symptoms, you find the chip, you replace those capacitors, and Bob's your uncle. Okay, does that make sense? Okay, that is a real important one. The 2 super important things about this part of the discussion is, A, the X-ray protector circuit exists. I guess 3. The Spanish Inquisition. The 3 things are, A, that the X-ray protection circuit exists, 2, that it's caused by the overvoltage condition, and C, that that problem is caused by that little capacitor located somewhere near the PWM controller often. Now, there was a customer notification on this particular monitor, the KT1703, where there was a different problem that caused this same exact symptom, and it turned out to be this little opto isolator. There is a problem with this KT1703 where this little tiny device, and I'm really kind of out of time on this, it's called an opto isolator, had some problems, and it was really not so much that the opto isolator was bad, but they made an engineering change that changed a resistor value. If you look through the back issues of Slot Tech magazine, I can't tell you which one it is. It was called Blooming Causes Blackouts. So if you have a Cortec KT1703, a Cortec monitor that's doing the same thing, going into X-ray protection, it doesn't use this exact same circuit. It uses this thing called the opto isolator. If you ever have that situation, just give me a call and I'll tell you what it is. Look through your back issues of Slot Tech magazine. You'll see an obvious reference to it it's real obvious. Okay, everybody okay on that? All right, so let's take 10 and 10 only because we really have a lot to cover. Come on back. And you know, even though we're actually finished with power supplies, just to show you in the real world what it looks like on the schematic, and again, in the lower right-hand corner it says Seiju Corporation. That's the one. That's actually the Cortec KT1703. Seiju, Cortec, it's really the same company. If you look in the lower left-hand corner, this is clearly the power supply. And I can tell that this is the power supply because it says AC input right here on the left-hand side. Where it says, you can see where it says AC input. You know, so if you follow those to the right, and we're just going to do this extremely quickly. I just want you to see where this is on the schematic diagram. You can see that the AC power comes in to the right, and it goes to the bridge rectifier, which is right here. The output of the bridge rectifier is filtered by the main filter capacitor. In this case, it's 220 microfarads, 400 volts, right there. See it right there? So this is the positive output of the bridge. It goes to the top of the transformer, and the bottom of the transformer goes to this IC module. You remember I said that in this monitor, and I showed it to you, that the FET and the PWM controller chip are included in one thing. It looks like a transistor, but it has 5 legs, and that's it. So that's both of those things. Looking at the output side, you'll notice that there are a number of outputs, and they're really clearly labeled. For example, here's a 125 volt output. That actually goes to the video output circuit, the video output transistors on the neck board. Well, if I wanted to test that 125 volts, where would I do it? Well, if I could find R116, I could check it at one end of that. The other end's grounded, so it'll be 0, so that would be one place. But that's hard to find. Diodes are much easier to spot. You look for the yellow transformer. Somewhere near it will be a diode labeled D116. All we have to do is touch the cathode end of that. You know, here's, well, let's just look at this one here, 61 volts. That's the B+. I want to measure that. Where can I do it? Well, I can't really do it at that capacitor because the leads are at the bottom on the bottom of the board. Where can I do it? Cathode of D109. Here's a 25 volt power supply, 26 volt. That goes to the vertical output circuit. Where would I measure that? Well, I can measure that if I could find this little coil, which is actually a little, it's called a ferrite bead, a little coil. It'll be labeled on the board, clearly BD104. I could check it there. Or I could really check it at the cathode of that diode. It would be more or less the same. 6.3 volts. That goes to the heater. Remember I mentioned several times that the heater is driven off of 6.3 volts. And so that comes from that winding right there. Where could I measure that? Well, if I found resistor 123, that sticks up out of the board. I could measure it there, or I could measure it at the cathode of D111. That would be a good place to measure it. You get what I'm saying? And here's 12 volts. If I could find R126, which is easy to find, I could measure it there. Or since it's only 10 ohms, if I went to the other side of it and went to the cathode of that diode, it'd be more or less the same. So, I mean, it's really actually pretty simple. And those diodes are the ones that I showed you previously. Let's look at them. You know, here's a diode right here. Diode, see if I could see in the light what diode number it is. D116. I just mentioned D116 to you. I forget which output it is. Which output is D116?